Good afternoon, everyone, and welcome. I'm Rick Lufkin, class of 68. 68 sounds like a long time ago, but it doesn't feel as long as the years may indicate. We shall see. It's an honor for me to serve as the chair of MIT's Cardinal and Gray Society. My wife, Ruth, and I welcome you to today's online lecture. Thank you for joining us. And when I mean all, I mean including both the Cardinal and Gray Society and members of the Emma Rogers Society also. A special thanks to the MIT Press for partnering with the Alumni Association for this event. I hope you're all enjoying this spring weather. The warm weather and what comes with it is exuberant. And while this hasn't been much of a winter behind us, I think we're all still looking forward to the new season. Every time I take part in a Cardinal and Gray event, whether in person or online, I'm reminded of the incredible power of our community. Though our journeys have been unique, we are united by the meaningful experiences, milestones, and memories we share from our time at the Institute. On behalf of MIT and the Alumni Association, I want to express my gratitude to all of you for continuing to honor and cherish the relationship we have built with the Institute and with each other. On a personal note, this event marks my last online gathering as the Cardinal and Gray Chair. My term ends on June 30th. While I hope to see many of you in person at tech reunions next month, I want to take a moment to express my heartfelt gratitude for allowing me to serve as your chair. I am grateful to have met and developed friendships with so many of you, and I continue to be inspired by your passion for science and technology, as well as your deep intellectual curiosity about the world. It has truly been an honor to chair this group. Thank you. It is now my pleasure to introduce Howard J. Herzog, a senior research engineer at the MIT Energy Initiative, colloquially known as MITEI. MITEI, MITEI. Howard's research delves into carbon capture and storage technology, CCS, supporting MITEI's quest for zero and low carbon solutions. His book, Carbon Capture, part of the MIT Press's Essential Knowledge series, provides an overview of CCS, promising that overlooked climate change mitigation pathway. Today, Howard will elaborate on the workings of CCS and its potential contribution to reducing the negative impacts of climate change. Please join me in welcoming Howard Herzog to explore more about carbon capture and storage technology. Howard?
Okay, thank you, Rick, and thank you to the Alumni Association and MIT Press for doing this along with the Cardinal and Gray Society. I'm going to first let me just welcome everybody online, whether it's whatever time of day it is with you. I'm going to just share my screen here. And good. So I think we're good to go. So I'm going to talk today about carbon capture and also about carbon removal. And in just a moment, I'll tell the difference about this. As Rick has said, I wrote a book, came out in 2018, on carbon removal for the Essential Knowledge series. And I have just put in a manuscript. Whoops. I've just put in a manuscript. My animation isn't working. Hang on. Okay. There we go. And I'm working on a new book called Carbon Removal. We just put in a manuscript last week. I have a co-author on this, Niall McDowell, and this book will come out scheduled for August of 2025. But I'll be talking about some of the things I talk in the book today. I just want to start with a introduction to show you where climate carbon capture and carbon removal fit in. And this is something I've used for a while called the climate diamond. And I think most of you are familiar with this. We have human activities, which put greenhouse gases in the atmosphere. This leads to a rise in our global temperature and all sorts of impacts on our Earth systems, whether it be extreme weather, sea level rises, etc. And these impacts on the Earth systems feed back on human activity. There's also another arrow between the atmospheric concentrations and the Earth systems, because There's constant fluxes between the atmosphere and the terrestrial biosphere and the ocean. And this can go in two ways. So today, the ocean and the trees and the vegetation are absorbing some of the CO2 we're putting up in the atmosphere. But in the future, they could go the other way. And for example, people talk about the warming of the permafrost up in the Arctic could be sending large amounts of, say, methane gas into the atmosphere. So those are the connections. And what we can do is people, we can have certain ways we can intervene in the system. One is mitigation of emissions, so we can put out less emissions. And this is where carbon capture and storage has a role as a mitigation technology, where we still burn our fossil fuels, but instead of letting the CO2 go into the atmosphere, we capture it and store it, usually in underground formations, which I'll talk about in a minute or two. Adaptation is another way we deal with this, and that's happening all over now, including, say, building bigger seawalls, for example, but a whole host of things on adaptation and on building codes for more extreme climates. And then there's CO2 removal, and I'll be talking about this also, where we try to move the CO2 from the atmosphere into other reservoirs in the earth, whether it's the vegetation and soils, or if it's the ocean, or if it's into the geologic formations. And finally, solar radiance management. I think there was just an opinion piece in the Globe, this Boston Globe this morning on this, which is a geoengineering type option, where we actually don't do anything with the CO2, but try to counteract the effect of the CO2 by changing the amount of sunlight coming in. Very controversial topic, which is outside the scope of discussion today. So let me jump right in with carbon capture and storage overview. People have asked, is this really possible? Can we really capture and store CO2? And the answer is yes. We're doing it today. All components, major components, are commercially available. But we're doing it at a limited level. And why is that? Because it's almost always cheaper to emit to the atmosphere than to capture the CO2 and sequester, which is quite costly. Therefore, opportunities are limited to niche areas until carbon policies are put in place. There's some carbon policies put in place that sort of enable some carbon capture projects to take off. And I'll mention some of those in a few minutes. So if we want to capture CO2, where are the sources of it? And there's a variety of sources. And as you see in the second column here, the concentration of the CO2 can vary in these sources. And depending on the concentration, it makes it how hard or easy it is to capture. So the easiest to capture is high pressure and high purity sources. High pressure sources include natural gas wells, where we can take the CO2 out of synthesis gas, which is produced in the production of both hydrogen and ammonia. High purity, an example is ethanol plants. We have a lot of ethanol plants producing ethanol via fermentation to be used for blending in gasoline. And that's a very good opportunity to capture the CO2 relatively inexpensively. When we get to more dilute sources, such as from coal-fired power plants, natural gas plants, cement plants, iron and steel, it gets harder. And we'll look at what that is. And now, when we talk about CO2 removal, people are talking about from extremely dilute, which is the air, and this is much, much harder. Even though we do some of this today, is necessary to maintain the living conditions in submarines and in spacecraft. So that's sort of the overview. This is a picture of air products and chemicals plant making hydrogen, and you can see, let's see if I can get and you can see here on the left those are that's the capture, though, that's using a vacuum swing absorption, and it could do it because it's capturing the CO2 out of a high pressure source. Most of the CO2 comes from atmospheric pressure sources, and so things like adsorption that really like a pressure differential become very expensive if you want to do it for what I call these dilute sources. And what people do for these dilute sources is use chemical absorption. Basically, it's a chemical that will react with the CO2 and have it absorb into the solvent. This is what we call post-combustion, is cleanup from the exhaust gas or the flue gas of a process. And the dominant chemical that's used is amines. Why amines is sort of like a Goldilocks solution. It's strong enough to grab the CO2 out of the flue gas, but doesn't hold it so tight that it's hard to get the CO2 off of the sorbent into the form we want. This is a schematic of amine process. We have two major pieces of equipment. We'll start with the absorber here, where you have the flue gas flowing up. You have a solvent flowing down, in this case, an amine solvent, usually 20 or 30% by weight, amine, and the rest water. There's some additives in there to sort of inhibit corrosion and things like that. As the solvent flows down, it's a packed column, so there's a lot of surface area in there for contacting with the vapor. The CO2 will from the gas will react with the amine solution and go into the liquid. We can then heat that liquid up, and the absorber operates about 50 degrees C. The stripper or regenerator here operates about 110 degrees C, and we heat it up, and that can drive off the CO2. It's used steam, so there's steam going up the column and the CO2 coming off. The higher temperature changes the chemical equilibrium to make it easier for the CO2 to come off. The steam creates lower partial pressures, also to help the driving force of the CO2 coming off. You have mainly CO2 and water up here. You can condense out a lot of the water and then send the CO2 to compression and dehydration. And then the amine that comes out the bottom of the column is reused back in the absorber. So that's how it looks. And what this is a plant, the Petronova plant outside of Texas. It's one of two power plants, at least in the U.S. and Canada, that's capturing CO2. It's a big plant. We're only capturing part of the flue gas. So the flue gas from one of these units, and you can see this pipe here, the flue duct pipe, is going into the absorber here and being captured. This captures about 1.6 million tons of CO2 a year. That's equivalent to about 250 megawatts of coal-fired power. So once we capture the CO2, we need to do something with it. And I should say there's other capture technologies under development, and there's a wide range, but so far for these atmospheric streams where the CO2 is dilute, say 10, 20% or so, the amines process is a very dominant process. But if you go into the literature, there's other ways that are being investigated, but due to time, I'm not going to go into detail on them today. Geologic storage is what we do with most of it. People ask, can you utilize the CO2? In theory, yes, but the problem is CO2 is basically spent fuel. It's when you burn a hydrocarbon, you get CO2 and water. And people say, well, we have like lots of hydrogen available, but most of that's tied up in water. To make it useful, you have to reduce the water. Same here. If you want, most uses of CO2 require energy, and so if you want to get that energy, when we use hydrocarbons, say we get the energy from the hydrocarbons. You can't get it from the CO2. You can get the carbon, but not the energy. And in most cases, the amount of energy you need to reuse that CO2 can be better spent else places. So utilization is going to be a very small part, I think, in what to do with the CO2. So we got to store it, and people store it in geologic formations. A lot of these are sandstone formations, the same type of formations that hold our oil and gas today. And so actually depleted oil and gas reservoirs can be used for this. The biggest storage volume is in these steep saline formations, where basically filled with briny water. A lot of work so far is used enhanced oil recovery, which is an active oil reservoirs. When you put CO2 down active oil reservoirs, it mobilizes the oil and gets a higher percent of the oil out of the reservoir. So a lot of the EOR and some of these CO2 a lot of the CO2 in some of these capture projects has gone for EOR to help the economics at the early stage of development. When we do put in these deep formations, we want to go below 800 meters, and that ensures one phase of the CO2 basically as a supercritical fluid. It's supercritical pressure, so around 80 bar. So that's where we get 800 meters. We get about 10 meters to a bar for the hydrostatic pressure. People are investigating other types of rocks, specifically mafic rocks, or these are basically basalts. There's a pilot project up in Iceland that's doing this. Is a little different. Here, they actually want the CO2 to react with the rock and form other rocks. In the case of geologic storage, we put it down as a supercritical fluid. When you're using the mafic rocks, what they do is actually dissolve the CO2 in water, so it doesn't. That keeps it so it doesn't escape, and gives it the time, the 1 or 2 years needed to react with the rocks. Unfortunately, when you dissolve the CO2 into water, which isn't that dissolvable, and you increase the liquid volume by a factor of 25. So that's a big challenge for going to mafic rocks. This is a picture of where sedimentary basins are around the world. So the darker it is, the better it is to store the CO2. You can see they're distributed around the world, but there are a bunch of white spots, say India, Japan. So not everyone has access to storage reservoirs, which makes the logistics a little more daunting when you're trying to do it there. A lot of the activity we see today has occurred where you have good storage opportunity, and that includes the Gulf Coast of the U.S., where we actually have about 5,000 or 6,000 miles of CO2 pipeline that have been put in place to satisfy the enhanced oil recovery industry. So what's driving carbon capture today? Well, there is some tax credits that were recently increased in the Inflation Reduction Act. So you can get about $85 a ton to inject CO2 into geologic formations for storage purposes. If you're doing it with direct air capture, we'll talk about it in a minute, it's even a bigger number. So that has spurred some projects, especially where it's easy to capture the CO2, say from ethanol plants. There's infrastructure funding from the Bipartisan Infrastructure Act, including setting up hubs. There have been hydrogen hubs, where one of the ways to make hydrogen is with natural gas with carbon capture. There's also what's called direct air capture hubs, which is helping to establish direct air capture, which I'll talk about in a few minutes. There's state programs that some projects have used, including the low carbon fuel standard in California, where you get the market price, but that market price has been ranging around $200 a ton of CO2. That's quite an incentive. So you could actually, if you use EOR to get out the oil from the ground, and you keep that CO2 that you use for EOR in the ground, that oil can be low carbon oil. So when you get that oil to California, you can take get the credit for it. There's stockholder pressure on large companies. There's been a lot of cash from technology companies, especially in carbon removal technologies. And we're talking billions of dollars here from these technology companies. And finally, I think it's a growing realization we can't afford to ignore climate change. And so something has to be done. And once again, that helps increase the activity. This is from the Global CCS Institute, showing their project pipeline. The dark blue are things that are operational, and I should say the x-axis here is in millions of tons of CO2 a year. So you can see we're doing about almost 50 million tons of CO2 a year are being injected right now through CCS activities. The lighter blue is in construction, and then you see development. The ones in green, early development, may be no more than a press release, so I take those with a grain of salt. But you can just see how the activity has increased in the past several years, as I think people are starting to take climate change more seriously and saying we really need to look at solutions. Of course, what you want to do for any of these technologies, you'd like to get them up to what I call gigaton level, at least 1,000 metric tons a year of CO2 to make a significant impact on reducing the amount of CO2 going in the atmosphere. So that's a quick summary of carbon capture and storage. I'll move now to carbon removal, and hopefully we'll have plenty of time for some good questions. So what carbon removal is now is taking it out of the air, and there's really only two ways to get it out of the air. One's biological, and these are what our trees do every day. And so we use biomass to help us capture the CO2. The other is chemical. In this case, we need a form of alkali, a basic material. Where we show the capture from point sources, we're using amine. Amine is an alkali material, basic. CO2 is an acid, so we have this acid-base reaction going on. The problem with alkalis, we don't have it lying around. If we have alkali lying around, the CO2 from the atmosphere will neutralize it over time. In fact, this is what happens with nature, with rock weathering. So you have alkaline rocks, they react with the CO2, but these reaction rates are on the order of hundreds of thousands of years. We want to look at reaction rates that are much quicker in using the alkali. So, and when we have it, we can store the CO2 in one of four reservoirs: the terrestrial biosphere, the ocean, geologic formations, as I just talked about, or creating rocks, as nature does with weathering, as people are trying to do using the mafic rocks for storage. An example of each one of these, we have afforestation, is one that's practiced now using the biological methods. People have proposed in the past using iron fertilization for the ocean. I think this is a non-starter because of all the environmental issues associated with it. We have something called bioenergy with CCS, and I'm going to be talking about that very shortly. For the chemical side, we can line the ocean. It comes under the category of what's called ocean alkalinity enhancement. This, once again, is I find it very interesting, but I think to implement it in the ocean is the governance of that is going to be a fairly significant barrier to overcome. Direct air capture, which I'll talk about in a minute, and then you can do enhanced rock weathering. Very simple way to do that is you grind and crush the rocks up, so there's more surface area for reaction. Of course, that's not inexpensive to get these particles as small as you need to have reasonable reaction rate. But I'm going to just talk about the two removal pathways that take the CO2 into these geologic formations. I will say on all of these have, what should I say, challenges. For instance, storing things in the terrestrial biosphere. Permanence is a big issue. How can you guarantee permanence, especially with the increase in wildflowers and wildfires and in, say, pestilence that we see in an increasing climate world. Whereas you can put in geologic formations, which are secure for many millennia. So let me start with BECCS quickly. So BECCS is really a good way to show the commonality sometimes between carbon removal and carbon capture and storage. Here, what we're doing is capturing the CO2 from a biomass fired power plant and putting that into a geologic formation. Why is that carbon removal as opposed to just carbon capture? It's carbon removal because the biomass took the CO2 out of the air in the first place. And so now we're taking the CO2 from the atmosphere to the biomass, then into the geologic formation for the CO2 that is released when we burn the biomass. Now, we don't have a lot of biomass fired power plants around because coal-fired plants were much cheaper for a couple reasons. One, biomass plants have lower conversion efficiencies because of all the moisture in them. They also have higher fuel costs. Now there's some cheap biomass fuel costs, waste biomass, and that's reducing the biomass plants such as in pulp and paper. This does require a sustainable biomass supply, saying that if we harvest biomass, we have to replace it with new biomass. And what drives this actually is the value of the carbon in the biomass, more so than the value of the energy in the biomass. And BECCS can act as a backstop technology, or any of these carbon removal processes can do that. What we see here is a couple runs from our big energy model at MIT. And if we don't have BECCS, we see, or any carbon removal, we see how the price goes up after we start taking care of the cheaper stuff. We still have a significant amount of emissions that are higher price, hard to remove. This can be from agriculture. It could also be from things like airplanes. Now, if we can offset that with a carbon removal, and we have enough of that at a fixed price, you see how it caps the cost of meeting climate change. And this is a big deal if that's true. So that's what we need. That's why people are so interested in these carbon removal technologies. We don't have enough today to see this type of behavior, but the hope is that this is what will happen in the future. So let me go next to direct air capture. And this is basically, once again, it's similar to the regular carbon capture in that we're taking CO2 out of a gas, except here the concentration is very low. No question we can do it. There's operational units today, and in just a minute I'll show you one. We have lots of money flowing into it. There's at least 30 new companies in the direct air capture space, and I wouldn't be surprised if there were over 50. I learn of a new one just about every week. But the real question is cost. And what's the cost today? It's $1,500 a ton of CO2 if you want to buy some offsets. I crossed out the $1,200 because that's what it was on the website a year ago, but it seems the price has gone up. And this is the website from Climeworks. They have the world's largest operating direct air capture unit, and you can do the arithmetic on this for how much you pay per month for how much CO2, and it comes out to the $1,500 a ton of CO2. Quite a big number, given that the European trading system is operating at $80 or so a ton of CO2 today. So it's a order of magnitude higher in cost than what we see for mitigation options today, which can be much less expensive. This is the plant in Iceland. These are two of the four. There's four of these units. We see 2 here. Basically, those are exhaust fans you see. So that's the back of the unit. The air is coming out the back of the unit, being sucked in through the front. There's basically filter packs in there, and those filter packs are filled with amines. They're solid amines. They're on a solid substrate, and those amines react with the CO2. Once the filter pack is basically saturated, they'll stop the emission. They'll put a plate over it and put a vacuum on it and heat it up a little to about 100 degrees and vacuum pump off the CO2. So that's operating at 4,000 tons a year right now up in Iceland. Now there's been a lot of interest in direct air capture, but nature says not so fast. There's 2 major challenges, and that's the large amount of air that must be processed and the significant energy use that's needed. So because it's low in I should say, because the concentration is low in the atmosphere, you have a very different type of absorber. This is from the Petronova plant that I showed you. And you can see the absorber here. That does 1.6 million tons of CO2 a year. This is an early version of a Climax plant. This does 900 tons of CO2 a year. You see the aspect ratio is very different. In Petronova, you have a tall column compared to its cross-sectional area. Here you have a very shallow absorber with a humongous amount of cross-sectional area. You'll need 1,800 of these units you see in front of you to process the same amount of CO2 as you see from the Petronova plant on the left-hand side here. So very massive equipment is one thing. And then in terms of energy use, first we have to realize we have to use low carbon or zero carbon energy. If we actually powered a direct air capture unit using the coal-fired power plant, we actually put up 1.2 kilograms of CO2 for every kilogram of CO2 we took out of the air. So that does us no good. It defeats the whole purpose. So you really got to use this close to zero carbon energy. And if this is an example, if we wanted to capture if we wanted to get enough emissions out of the air, enough direct air capture for 20% of our US emissions, which is about 1 billion tons a year, total US emissions around 5 billion. That's that red line. And we can see here in 2019 electricity production. And if we're going to use just the zero carbon sources, we need about 80% of the zero carbon energy produced in the US today to capture just 20% of our CO2 emissions. But what we need to do is we want this low carbon energy to replace our coal and gas use in our electricity system. If there's nuclear retirements, we want those replaced. We want to charge our EVs. We want to power our heat pumps. We want to produce green hydrogen. And now we need to power our AI servers, which are taking tremendous amount of electricity load, so much so that we see an increase in overall electricity use happening in the United States, and it's projected to continue. So there's a lot of competition for this zero carbon energy, which says, are you going to be able to get enough of it? If you can, what cost? And see, even from a viewpoint, is that the best way to use this to get us to a net zero carbon system? And the answer is probably it's better to use that lower carbon energy to do some of the other things listed on the slide. So with lots of money flowing to direct air capture, in the development of new companies commercializing DAC, why is that? Well, if you read the literature, there's a lot of articles saying we can do this for $100 to $300 per ton of CO2 removed. And I don't find these estimates at all credible. And I've written a book chapter where I tried to figure out what it would be. And I think optimistically in 2030, if we can be in the range of $600 to $1,000 per net ton of CO2 removed, we'd be doing well. So I think, the bottom line is, I think negative emissions are very important. There's lots of ways to do them. But I think the interest and money going into direct air capture today is creating a bubble that's going to burst somewhere down the road. And I'm going to finish there. And I think I left a lot of time here for questions.
Thank you, Howard, for the fascinating discussion and for sharing your insights into carbon capture's potential for climate change mitigation. We have 20 questions listed so far, but I'm sure we can get some more. Let's take a look and see what people had to say. At the very beginning, in fact, even before you started speaking, someone felt they had to bring up some of the raw statistics. The world CO2 emission is 4 million tons per hour. How much can CCS help to reduce?
No. Yeah, that's an interesting way to put it.
Yes.
I look at it that the world puts out. Trying to think of the number. It's a 36 billion. I think it's about 36 billion tons a year of CO2, and there's no silver bullet. Nothing's going to take care of all of it. And I like to think that carbon capture, if it can be a 10 to 20% solution, that's a major contribution. And I think a realistic one. So if we saw where we were today, I think that slide I'd show we're about 50 million tons a year. So maybe, and that's like 1/10 of 1% now of the total emissions. So we have a couple orders of magnitude to come up to get to that 10% over time. It will not happen overnight. As we see getting our overall CO2 emissions down is we're still going up instead of coming down, despite trying to bring it down for 30 years. So nothing goes quickly, but hopefully we start seeing the bend of the curve soon.
Here's a comment that sounds almost too good to be true. Quote, I read of ancient trees captured so much carbon so rapidly that it led to mass extinction event 252 million years ago. Do fast-growing plants have a role in reducing CO2 levels?
Well, I'm not familiar with that event. I had to learn a little about trees to write my book. I think biomass is being underutilized. I'm not sure how much we can get, if we just did, say, afforestation and reforestation type projects. I sort of like the sustainable harvesting of the biomass, whether it's used for bioenergy and CCS, or you can use it in biochar as another example of things you could do. I think that has great potential. Once again, it's hard for me to say exactly what that potential is. I think the point is, how do you do the sustainable forestry from the CO2 things? And the sustainable forestry can also help in other ways. And people talk about, getting rid of a lot of the fuel in the forest that contribute to these wildfires. So I think there's a lot of potential for biomass. Once again, nothing's a silver bullet. It won't do it by itself. But people today say, not one number from reporting. You got to be careful because it's hard to understand what they mean in context. They said that 2 billion tons of CO2 today are being absorbed from managed forest. some of that's going into, like, I think the number I remember is 400,000 of that. What did I say? Yeah, 400 million of that is going into things like lumber to produce wood, so they count that as long-term housing. But it's but while that's going on for managed forests, we're also losing CO2 from deforestation. So I'm not sure what the net is on that, but definitely forests can play a role.
One person asks, what about using artificial photosynthesis?
That's when I first went back to MIT in my position. There was a professor in chemistry. I think he became provost at one point, Mark Wrighton. That was sort of his bailiwick. It's people have worked on it. I haven't heard much recently. But when people are working not just on artificial photosynthesis, but they also work on a cell to make this to make sunlight into hydrogen. That's sort of like a holy grail, but it's not ready for prime time yet. It's been explained to me it's very difficult chemistry. But people are working on it. I don't have an update on where exactly it's at.
The ocean seems like a bad choice for carbon removal since it already is taking on more than it can handle. And someone else has further commented on that. I agree. Planet health depends on removing excess carbon from the ocean that was added to the ocean over the last 100 years.
So, the ocean's interesting. So basically, the ocean has roughly 40,000 gigatons of CO2 in it, compared to the atmosphere, which has, I think, a little under 1,000 gigatons. It has almost 60 times the amount of carbon in the ocean. Most of the carbon in the ocean is in the form of carbonate and bicarbonate. With the CO2 going into it, it is increasing, and that's acidifying the ocean. So the two main methods that people talk about with the ocean, one is iron fertilization, and that's really looking at getting organic carbon in. So the idea there, you put iron in, you have these big phytoplankton blooms, and then some of that organic carbon will go down into the deep ocean. Questions about that is A, how much can really go in the deep ocean? B, if you add iron here using other nutrients, is that going to be robbing those nutrients from other parts of the ocean to make its productivity go down? And finally, you're totally changing the ocean environment to do this. And is that at all a reasonable thing to do? You get all sorts of things like anoxia, a change in species. So I think that's sort of dead on arrival. People liked it because they thought it was real cheap just to throw iron in the ocean. And nature does this itself. When the wind blows off the Sahara, all sorts of things gets deposited in the ocean, but that's a much smaller quantity. The other one is ocean alkalinity enhancement, where we actually put alkalinity in the ocean, let's say in the form of lime, calcium hydroxide, slacked lime. And there, what happens is that will react with the CO2, and actually it will react with about 1.7 molecules of CO2 for every molecule of the calcium hydroxide, because it eventually ends up as carbonate and mostly bicarbonate in the water. And it also has a plus of counteracting the ocean acidification. So it actually makes the ocean a little more alkali. And the question is, can this be done in a good manner? So you're changing the overall alkalinity of the ocean. And maybe we do this on a massive scale. You're talking about maybe a 1% change of the ocean alkalinity, but it has quite a few benefits. I sort of am intrigued by it. I think there's a lot more work has to be done to see that it's safe. But once it's in there, and basically once you get enough of those, you're adding these calcium ions or maybe sometimes magnesium ions to the ocean, they stabilize it, and it could stay there for a long time. So I wouldn't write it off so easily. I don't think something would happen overnight. And I think this ocean alkalinity enhancement is a form of geoengineering, and any form of geoengineering, you got to go slow. But in some ways, I think it's a little more, to me, it's a little more interesting than say I sort of like it a little more than say throwing up sulfate particles in the atmosphere. But anyways, so that's where the idea of the ocean coming in. It's a big sink already, and it is capable of doing more. So,
what is the cost of CO2 capture in dollars per ton and as a percentage of energy required divided by energy produced for various energy generation methods?
okay, good question. And so, from a power plant, let's just take a coal-fired power plant. What happens there is you'll need somewhere, you'll derate the power plant. In other words, the net electricity output will fall somewhere by about 20%, maybe a little higher, depending on the method you use. The cost, we've done a lot of work and we think like nth plant costs, once everything's set up, will be like $65 a ton of CO2. But today, since we've only done one or two, you're still to have a lot of first mover costs. We don't have a supply chain in place. It's going to cost over $100 per ton of CO2 to do projects, these initial projects on there. Natural gas plants is a little more dilute in concentration. It costs a little more, maybe 20% more. Actually, from an energy viewpoint, it's not quite as bad because you don't have as much CO2 per unit of energy to capture in a power plant. There's a lot of work today looking at cement plants, and why people like cement plants is because about 60% of the CO2 in the cement plants comes from the limestone that you calcine, not from energy. And so you're not going to be able to really stop doing that with anything but carbon capture and storage. So that's a pretty good fit. Cement plants, there's a couple of pilots going on. Every one of these new plants presents some challenges. The amine systems really dislike impurities, and every different type of flue gas has different impurities you have to clean up first and see how that works. But once again, it's more of a outright energy use. You're not derating the plant; it just becomes a capital cost. I showed the number on direct air capture, and once again, it was given in a second law in a work type thing. So you can have both heat and power do it. But if it's on a pure power basis, that was about 1,200 kilowatt hours per ton of CO2. If you're doing it from say a cement plant or a coal-fired power plant, that number is closer to $300 per ton of CO2. And that includes compressing the CO2.
Do you consider Blue Planet's plan to create synthetic aggregate practical and/or scalable?
I can't comment on that because I'm not familiar with the process.
Okay. In the chart showing the growth of CCS, what explains the dip in the middle years?
Okay, so basically we hit a peak in about 2008, 2009. CCS for a couple of decades the interest was increasing. There were in 2008, what was going on? There was a climate change bill in the Senate. I think it was the McCain-Lieberman bill. It People thought we were going to actually have climate legislation. Obama got elected president. And then instead of doing climate first, he did healthcare first, spent all his political capital. Also, I think it was in 2009, was the Copenhagen meeting that was supposed to produce a protocol to replace the Kyoto Protocol, and that just fell apart. So both nationally, internationally, climate change policy went into the wilderness, and these companies said, I'll pursue this technology, but if there's no climate policy, I don't need it. So I don't know when or even if, we're going to get that. And the political signals were all saying, we're not going anywhere on this. And that didn't pick up until about, say, near the end of the 2010s, when you started having reports like the IPCC report on 1.5 degree warming and other things saying we can't ignore climate anymore. And then you started getting some more legislation in the US on giving incentives, and that's sort of make it rise again.
Can the sulfur emission scrubbers on power plants be used for CO2 removal?
So when you use amines, the sulfur poisons the amines. So you've got to use the sulfur first. You got to get rid of the sulfur first. So those SO2 scrubbers are important. And in fact, sometimes, like at the Petronova plant, where they had SO2 scrubbers, it didn't clean it enough, and they had to put an extra scrubber on the front of the CCS unit. People have talked about trying to do these together, but so far, nothing. They're both acid gases. The thing is, SO2 is a stronger acid, and it really sticks to the base. If you remember the slide I showed the on the amine process, I didn't talk about but there was a regenerator unit there, and what that regenerator unit was to regenerate amines that basically got poisoned by the SO2. You can regenerate them, but not just through a simple thermal swing. You have to do it chemically, and that's a little more expensive.
Biological removal of CO2, how much comes back from plant matter after it decays after dying?
Say that again. What's the beginning of the question?
Hang on. I think I lost that question already.
Oh.
The question was that if CO2 is captured by plants, but then how much of that just gets back into the atmosphere as the plant dies and decays?
Right. So I mean, if you look at the data from Mauna Loa, which shows the CO2 concentrations going back all the way to the 1950s, we see a steady upward climb. But if you look closely, every year there's wiggles. So it goes up and down, up and down. And what that is, in the spring, the plants in the Northern Hemisphere are actually bringing the CO2 concentration down by 1 or 2 ppm. And then when they die, it decays and goes back into the atmosphere. So what we need to do, if you're going to use plants for CO2 removal, you've got to, and you want to make them at least somewhat permanent. That's why permanence is an issue. You've got to sort of keep the stock of biomass on a given piece of land constant. So anything that dies off and sends CO2 back has to be replenished by new growth in the trees. So that's how plants work. So what we're doing, the flux between the atmosphere and plants is on the order of 100 million tons a year. And so we're looking at small differences in that. So really what you look at, it's the stock of carbon in a certain piece of land and how you can grow that stock of carbon over time, even though there will be fluxes from that land to the atmosphere. It's really what's the net amount of carbon held on that land.
Here's a question that seems to challenge the very idea of the importance of CO2 removal. Quote, why the necessity of CO2 capture in light of Dr. Stephen Conan's basic conclusion, Unsettled, the title of his recent book concerning published government analysis of post-1850 data with respect to CO2 emissions driving up global temperatures or causing extreme weather conditions. Previously, the UN IPCC First Assessment Report in 1990, page 15 of the policymaker's summary, stated variation in temperature closely correlated with variation in greenhouse gases. Much page 202 stated this period around the year 1000 of widespread warmth is notable in that it was not accompanied by an increase of greenhouse gases. Both the warming and the subsequent cooling without change in greenhouse gases were effectively affirmed in 2012.
Well, I mean, there's a whole different lecture to talk about, but I mean, I think it's pretty clear that that the greenhouse gases we're putting is closing global warming. The latest IPCC report basically said, it's a certainty that this, the bulk of this warming is caused by human activity. We can see what's happening with the warming on the, we can see the effects of the warming, whether it's in unprecedented ocean temperatures, which could lead to a pretty heavy hurricane season this year. We see the sea level rising. So we see everything sort of fits together. The timing and magnitude, there's uncertainty in, but I don't think there's any doubt of the human activity of emitting greenhouse gases. The atmosphere is leading to this warming. If it was just natural sources without changing greenhouse gases, we actually should be on our way to our next ice age, which we are not.
How much would have to be processed by direct air capture to remove 1 gigaton of CO2 per year, assuming a 100% capture rate?
How much air?
Yeah, how much air?
Well, I don't have that number. I do have, let me see, I can look up very quickly here. If I have this. Yeah. I think I can find it quickly. It's right here.
I'm afraid time is.
Why don't you give me the next question while I'm looking it up?
Is there a role for algae, particularly genetically engineered algae that can more aggressively process CO2?
Yeah, this is algae comes up all the time. It's very difficult. It's really a cost issue on the algae. Why people are interested in algae, its net primary production is about 10 times faster than, say, typical plants, but it needs a lot of care and feeding to do it. I know one of the real experts at it, and he says that you really got to do it in open ponds. If you try to do it in bioreactors, the cost goes out too quickly. There's been dozens of algae companies that have come and gone over the past couple of decades trying to make it work. So I'm not an expert on algae, but I will say people have tried, and we really don't have any real successes. And I just think it's something that's very difficult, and things can change. People have looked at bioengineering different algae and the like, but to date we haven't been able to overcome the challenges associated with that.
Howard, our hard stop at 2 is 30 seconds behind us. I'm afraid we must bring this to a
Oh,
conclusion. Thank you very much for your time and energy. And there are so many unanswered questions here that it just reinforces the importance of the subject. To learn more about Howard's book, the plug here, Carbon Capture, please visit the MIT Press website. Once again, thank you for being here today. I am profoundly grateful that our group continues to learn, explore, and celebrate together, even many years after our graduation from MIT. Please enjoy the rest of your day. Thank you very much, ladies and gentlemen. Good afternoon.